This is section 12.4, mathematical induction. We'll begin with learning how to prove a statement using mathematical induction. So what does that mean to use mathematical induction? Well, some sequences may be neither arithmetic nor geometric. So we have no formula readily available to evaluate the sum of the first n terms. So we need a way to find the sum of the first n terms. So we might consider evaluating the nth partial sum for several values of n to determine if a pattern exists. So basically, we will look at the nth partial sum, and then we will look at p sub 1, p sub 2, p sub 3, p sub 4. All of these are our partial sums. And then what we will do is we will speculate that p sub n is equal to n times n plus 1 divided by 2. So how do we prove that our hypothesis is true? We use the principle of mathematical induction. So we'll let p sub n be a statement involving the positive integer n and let k be an arbitrary positive integer. Then p sub n is true for all positive integers if these two things occur. If p sub 1 is true and the truth of p sub k implies the truth of p sub k plus 1. It's a little bit confusing in the definition, but once we work this problem, then we can go back and take a look. So in number 1, they've asked us to use mathematical induction to prove that p sub n is equal to n times n plus 1 over 2. So in part 1, we want to show that p sub 1 is true and p sub 1 is equal to 1. In part 2, we're going to assume that p sub k is true, and then we're going to show that p sub k plus 1 is also true. So here we go. We're going to assume that p sub k is equal to k times k plus 1 over 2 is true. So now we want to show that p sub k plus 1 is equal to k plus 1. See how we've added 1 to k here? So we're going to be adding 1 to this k also, and adding 1 here, you guessed it, will give us k plus 2. And then dividing by 2. And we're going to show that p sub k plus 1 is true. Okay? So let's go ahead and take a look here. So we have 1 plus 2 plus 3 plus so forth. And we're going to go to the kth term. And that's k times k plus 1 all over 2. Move that down just a little bit. Okay? Then we have 1 plus 2 plus 3 plus, we're going to go to the kth term, and now we're going to go to the k plus 1th term. So we had the kth term, and now we're at the k plus 1th term. So now we're going to say that this is equal to k times k plus 1 all over 2 plus k plus 1. And that comes out to be k times k plus 1 over 2 plus 2 times k plus 1 over 2. And so let me just make sure that you can see that. If we have, and now we'll go ahead and have k squared plus k plus 2k plus 2 all over 2. And as you can see here, we have k squared plus 3k plus 2 all over 2. Let's see if I can bring this up just a touch. And so, I'm going to fix that too. And now, as you can see, this is equal to k plus 1 times k plus 2 all over 2. And that is what we were trying to show was true. So it's a pretty straightforward method. We make an assumption. I'm going to bring that up just a little bit so we don't cut off this page. So we assumed that this was true right here. So we said that this right here was k times k plus 1 divided by 2 from this statement right here. And then we still had our k plus 1 term. Okay, so mathematical induction can be used to prove summation formulas involving powers of the first n positive integers. So we have some sums of powers shown here. This is 1 added to itself n times, and we end up with n. So some of these sums of powers are handy to have. You can see that the sum of I, which would be what we're counting with, 1, 2, 3, 4, that is going to be n times n plus 1 over 2. So the sum of the first n terms, I going from 1 to n, and so forth. You can see I squared and I cubed. So let's use mathematical induction in number 2 to prove that 2 is a factor of n squared plus n. So the first thing we're going to do is we're going to let P sub n be this statement. Two is a factor of n squared plus n. So we're going to assume that. Okay, that's our statement. Now we're going to say P sub 1, we're going to say 2 is a factor of 1 squared plus 1, which is equal to 2. So 2 is a factor of 2. So now we will assume that 2 is a factor of k squared plus k. Of course, this is our P sub k. And now we're going to have to show that 2 is a factor of k plus 1 squared plus k plus 1. And this is our P sub k plus 1. So how are we going to do this? We're going to state that k plus 1 squared plus k plus 1 is equal to, and now we're going to FOIL this, k squared plus 2k plus 1, and then now we have our k plus 1. Okay, so this is equal to this, and this is equal to this. And that equals, you can kind of look at that, is equal to, I'll put it under here, k squared plus k k plus 2k plus 2. And the reason why I wrote it like that was because this is divisible by 2, and this is also divisible by 2. So here and here. So now we can say that k plus 1 squared plus k plus 1 is divisible by 2. So 2 is a factor. Okay. So sometimes that can get a little bit complicated. Maybe read through that a couple times and see what you think. And now we will end this section by proving a statement using the extended principle of mathematical induction. And so we're going to let P sub n be a statement involving the positive integer n. And then P sub n is true for all positive integers n greater than or equal to j if P sub j is true, and for some integer k that's greater than or equal to j, the truth of P sub k implies the truth of P sub k sub 1. So let's take a look at this. The first thing we're going to say is that P sub 1 is equal to 2 to the first power, which is greater than 1. And now we're going to assume 2 to the kth power is greater than k. And this is our P sub k. And now we will show that 2 to the k plus 1 power is greater than k plus 1. And this is our P sub k plus 1. Okay, so now we have 2 to the k plus 1, and that's equal to 2 to the k times 2 to the first power. And that is going to be greater than k times 2. And why is that greater than k times 2? Because 2 to the k is greater than k. And I should have put a k times 2. And that is equal to 2k, which is equal to k plus k, which is greater than k plus 1. Therefore, 2 to the k plus 1 is greater than k plus 1 for any k greater than 1. Okay, and that concludes this section.